I'm going to present applications to protein adsorption, ion partitioning, electrostatic behavior of cell walls, using two different approaches, the classical charge regulation model and what we call charge-regulated volume charge density. Okay? And I'd like to discuss a little more about bispherical coordinates that I'm going to use to obtain some of the results presented today. This coordinate system started being studied by Hoskins and Levine in 1956. But then it was applied to calculating the force between two spherical particles in 1994. And in 1996, the same authors, Stankovic and Carney, expanded for two dissimilar spheres. Okay, so with this coordinate system, we can study two spheres of different size, or a sphere and a plate. So these are the coordinates. Don't bother about the expression. When we solve the Poisson-Boltzmann equation, actually the computational effort for this coordinate system is almost the same as for Cartesian. We only need to change some functions when applying, for example, finite volume method. So it's not a big deal. And just to show you a representation of this coordinate system, we have, of course, three variables, but I only present two here because in the third one we have symmetry in our system. There would be the psi. So surfaces with constant theta are apple-shaped like this. If theta is between 0 and pi over 2. And if theta is greater than pi over 2, it's kind of spindle-shaped, as you can see here in the middle. Okay? And surface with constant eta are spheres. So we have here eta greater than 0 in this sphere and eta lower than 0 in this sphere. Okay? So as I said before, we can consider different size spheres. It's no problem. Different magnitudes of eta. Okay. So using this coordinate system, we can transform this kind of grid of a more complex geometry in a much simpler grid. So when we are solving, numerically solving, we are solving this grid, not this one that is much more complex. And as you can see here, when we apply this kind of coordinate system, we give more importance to this region between the two spheres. You can see that we have much more points there than here outside. And this is very good because this is where the most change happen. Here we have the math of this coordinate system, but I think you don't need to worry about this. It's not that complicated, as I said, and we have to solve this nonlinear system here in order to obtain the variables. And once we have solved the Poisson-Boltzmann equation in bispherical coordinates, we get that electrostatic profile, as I showed before. So we have psi as a function of position. And by integrating this electrostatic potential, we can calculate directly the force between those two spheres. So this is the expression derived for in this case, I think it's already for two dissimilar spheres. Okay, so for a sphere and a plate, this integral, yeah, it is for dissimilar spheres. For a sphere and a plate, we do the integral over the surface eta equal to eta 1 over 2. Remember that in this case, eta goes from 0 to eta 1. So it's a kind of mid-distance. And for a sphere, geometry, we evaluated at eta equal to 0, just returning here. Eta equal to 0 is this plane. Okay. Okay, so going on. And by using this kind of this theory in this kind of coordinate system, we can address the interaction between two colloidal particles. Because now, when we apply this coordinate system, it's like if we were calculating the interaction between two plates numerically, but we obtain the result for two spheres. So we can account for the interaction between ions and spheres, and then after calculating in the whole domain, we get the potential of mean force between those two spheres, as I showed in the previous talks. Okay, so we get this kind of result. For example, here we have the distribution of iodides around two charged spheres. We have the first sphere is negatively charged, so we can see that we have a lower concentration here around this sphere because we have anions. And the second sphere is located here, is positively charged. We can see that at the vicinity of this sphere, the concentration rises. And here we can see that in between there is a kind of competition of effects, and we can see that as the magnitude of the negatively charged particle is greater, it wins the competition. So we have a decrease in concentration of iodide here. And from these results, by integrating this result, we get the force between those two particles, okay? And we can apply this for biological systems as well. For example, we can apply for two globular proteins. Remember that we are considering a very simplified model, of course, because we are simplifying, saying that the protein, the globular protein, is a sphere with its charge uniformly distributed around its surface. Okay, so we have here, for example, it can be two lysozymes interact, or a lysozyme and a BSA, as I showed yesterday. And we get those kind of results. This is exactly for lysozyme and BSA. So this is BSA, this is lysozyme. The pH is 4.5. And remembering the isoelectric point of both proteins, we can remind that lysozyme is more positive than BSA in this case because its pI is around 11.2. So we have a greater concentration, a higher concentration of iodide around lysozyme than around BSA. But in this case, both are positively charged. And by integrating the electrostatic profile, as I showed before, we can calculate the potential of mean force, or at least the Poisson-Boltzmann contribution, the electrostatic contribution of the potential of mean force. Let's remember that we are talking about the modified, the LVO theory, and we have this contribution. So we are calculating this contribution, the electrostatic contribution, and we get those kind of results. We can see here that with the modified Poisson-Boltzmann equation, considering dispersion interaction between ion and surfaces given by Lifshitz theory, as I showed before, we get very good ion-specific effects. We can see that the results are very different for different salts. Again, NP stands for the non-polarizable ion. There is the ion considered in the classical Poisson-Boltzmann theory, okay? So, and from this potential of mean force, integrating, again, the potential of mean force can be obtained, for example, integrating the force as with the expression that I showed before. Let's return a little here. So once we obtain psi as a function of position, we do this integral and get the force. Then by integrating the force as a function of the distance between the two particles, we get the potential of mean force, the energy between the energy of the systems containing two particles, okay? So we add the Hamaker contribution and the hard sphere contribution, and we finally get the total potential of mean force that we can introduce in this integral in order to obtain the second order osmotic virial coefficient. The osmotic second virial, sorry, the osmotic second virial coefficient. Why is it important? Because the fact that it's negative or positive is directly related to the stability of the proteins, to the solubility of the proteins, okay? So if you have, for example, a second virial coefficient positive, you have stability, and if it's negative, you have attraction, so you have coagulation, instability. Of course, we are neglecting the many-body interactions. We are only considering the two-body interactions, interaction between pairs, okay? And we see here, those curves stand for different Hamaker constants. In the literature, there are many propositions, different propositions of the value of the Hamaker constant. We considered all the whole range of Hamaker constants proposed in the literature. We didn't try to adjust any parameter, so we have all these curves are totally predictive. And we see that until at least 0.5 molar, we get very good results comparable to the experimental results. We were not expecting that it should work above 0.5 molar, because what we have here is a modified Poisson-Boltzmann theory, but modified only by considering the dispersion interaction between ions and interface, not considering, for example, ion size or ion correlation, okay? So when we increase concentration, this theory is not valid anymore. So that's why it doesn't work in this region. You may say, oh, but if we consider here a Hamaker constant of 10 kT, this one, we get good results. But this is a compensation of errors. We cannot say that it's a good result. It's not because it agrees with the experiment that it's correct. So in this case, we believe it's a compensation of errors. Even here, a so simplified theory was not supposed to work so well. So we still believe that it's a compensation of error. But there are other results obtained with the same theory that shows that it works very well for this kind of system. Okay, and I'm going to show more results in the next slides. So here we have the ion-specific effects. So we're considering the same conditions, pH of 4.5, lysozyme at temperature of 298 Kelvin. We get those results for different salts. So once again, we can see now for the second virial coefficient, we can see, again, ion-specific effects. So different salts are more or less effective in coagulating proteins. So we can see here, for example, that for sodium iodide, we have a more attractive interaction. So we would need a lower concentration of sodium iodide in order to precipitate the protein. Okay. And from the potential of mean force, we can also apply, by applying, for example, a first-order perturbation theory, we can calculate phase diagrams. So I present here, for example, a phase diagram for lysozyme at a fixed concentration of 0.3 molar, at the same conditions that I presented before. And we can see here that we have, once again, ion specificity. Okay, so this is a solid liquid-like equilibrium. So if we take a temperature here, we have this liquid-like phase in equilibrium with the solid-like phase. Okay, and this dotted line stands for a metastable fluid-fluid equilibrium, and this is the critical point. So we predict a metastable fluid-fluid equilibrium here and a stable solid fluid-like equilibrium. Okay, and this is the packing fraction. There is the volume that really is occupied by the protein. Okay, and applying the same theory, those results that I presented before, they were published some time ago in 2008, but then 10 years later, a student came to the same system and used the same program that I had prepared before in my PhD thesis, and he applied to study protein adsorption, chromatographic purification of proteins. So we have a system of a sphere and a plate. Okay, we consider that the adsorption is a flat surface, and the protein, once again, the globular protein, is considered a sphere. And applying the same theory, we get very, very good results. Once again, we didn't use adjustable parameters. Okay, it's a predictive theory, and here we have the results of Henry constant. There is the constant of the linear equation of state. If you consider, for example, that the adsorbed quantity is equal to Henry constant times the concentration. It's a linear isotherm. So this is the Henry constant predicted. And we can see that we predict, these curves are our predictions for different pHs. And the dots are different experimental results from different authors. So we can see that for monoclonal antibody on fractal gel, we get very good results. And applying for other systems, for example, this other enzyme, I won't try to say it, to pronounce it, on another adsorbent, we get, again, very good results. And once again, it works very well. I'm not saying that the theory is completely correct. You followed, I hope you followed until the first lecture, that there are many simplifications here. But it works quite well for this kind of system. We showed that for second virial coefficient, osmotic second virial coefficient, and now for adsorption of proteins, for sphere, and for sphere in a plate. Okay, it's important to consider this kind of coordinate system because we get the correct geometry of the system. And we have applied also, solved also the Poisson-Boltzmann equation in spherical coordinates. So we have another very simplified model here. We are trying to model the ion partitioning this time in a solution of lipids. And our lipids are simple spheres. Okay, you may get surprised with this. Is it going to work? I was not expecting that it should work because we are considering that we have simple spheres and that they are far from each other so that the double layer around this sphere does not affect the double layer around the other sphere. And from this, we try to calculate the ion partitioning in the system. Okay, so we have a concentration of ion here in this volume where there is no lipid-like particle, and another concentration of ion here where there are lipid-like particles. So what's the result that we got? We got this kind of result. So this is the concentration of ion in the up phase, and this is the concentration in the down phase. And we can see here, comparing with the experimental results, considering, for example, we consider different models for water, and the Sneers model gave better results. And here we have our prediction, and this is the experimental data. Of course, it didn't work quite, so well, but I was explaining much less than that. At least we got almost the same magnitude, and we got the correct qualitative results. So this is the polarizability of ions. So I think this is sodium chloride. No, this is chloride, bromide, and iodide. Okay, and we could get this qualitatively well, these results. And we can apply this for other biological systems. So again, I'm applying Poisson-Boltzmann equation. Here we have the boundary conditions considering the charge at the surface and the charge at bulk equal to 0. Note that this surface density of charge, surface charge density, in this case depends on psi, because we are using charge regulation model. So we have to solve this iteratively, as I already said, because we need an initial gas for the surface potential. From the surface potential, we apply charge regulation and calculate the surface charge density, and solve again to find the potential profile. And from this, we get another surface charge density, and so on. And when it converges, we get this kind of result, okay? The electrostatic profile near to cell wall, for example. So here we are applying to Saccharomyces cerevisiae, okay? So we are trying to predict the electrostatic behavior of Saccharomyces cerevisiae with this simplified model. So here we have cytoplasmatic membrane. You probably know much better than me. Periplasmatic space, ketene and beta-glucan layer, and a glycoprotein layer where the surface charge is located. So these glycoproteins are protonated or deprotonated, so they can be ionized, they can be charged. So here we try to calculate its charge. And how do we do that? We use charge regulation model. Okay, and two important parameters to characterize the surface groups are the number of groups, the number of each group, and the dissociation constant associated to that group. So here we have a table with the density of the density of sites for each group, and here the pKa range for each of these groups. These are obtained from potentiometric titrations experimental results. So we got those results from these authors, and we can see that we have a range here, a range of pKa's, and we can consider a fixed pKa in this range, or we can, if necessary, try to adjust and find the best pKa in this range, considering the uncertainty of these experimental results, okay? And just to revise charge regulation model, Fernando already presented, I talked about it too. So we have those equilibrium equations. We are once again approximating activity by concentrations, and we should remember that this is the surface concentration of hydrogen that depends on the surface potential, the surface electrostatic potential, okay? So the full expression to calculate the surface charge density that enters for now in our boundary condition is this one, and this is the expression to calculate the surface hydrogen ion concentration. Okay? Any question until here? Okay, let's go on. I hope you're not starving. You can follow me. And so let's go on. And using the same model, we can predict, we showed that we can predict, for example, Donnan potential. There is the difference of electrostatic potential across the membrane or across a barrier between two phases with different charges. As we have semi-permeable membrane, we have different charges inside and outside the cell, for example, does give rise to a Donnan potential. And we showed that we can predict this Donnan potential exactly equal to the Nernst, that predicted by the Nernst equation, using a continuous approach. Usually in the literature, what people do is trying to predict the Donnan potential by fixing the concentration of ions inside and outside the cell. So they say that they are reproducing. But we could do that by using a continual approach, and I'm going to show some details in the next slides. And Natalia is going to talk about this today in the afternoon as well. Okay. So we have here our modified Poisson-Boltzmann equation, modified because we considered fixed charge here, but not dispersion interaction this time, okay? As I said, we have a continuous approach, so we solve the same equation inside and outside the cell, okay, it's continuous. So this time our boundary conditions are these ones. The derivatives are 0, minus infinity and plus infinity here, because the interface is not our boundary anymore, as we are solving for both sides of the membrane. Actually, in this case, we are solving for the cell wall and the region outside the membrane. So we are expecting to get those kind of results for psi, and then we can calculate the other properties, as for example, Zeta potential that I'm going to talk later. So now that sigma that we used before in the surface charge regulation model is substituted by those fixed charges. So we consider fixed charges in this region, but not in this region. And here we can consider, for example, that they are uniformly spread here in this region. Okay, that's why in the boundary condition we don't have sigma anymore, because it's here, not here, the first boundary. Okay. Any doubt about this? Did you get it? So I'm comparing here the second model that is called charge-regulated volume charge density. We have now a volume charge density of fixed charge here, rho f, and the other one was the surface charge density regulation model. Okay, in that case we had surface charge. We considered surface charge density. Now we consider the volume charge density distributed in the cell wall. And in order to apply this in a continuous approach, we need a kind of smoothing function, because we have a discontinuity of concentration, so we need to do it continuously. We can use many different functions for that, and we chose this one, a kind of hyperbolic tangent function, so that we have always a continuous function. That's because Poisson-Boltzmann theory is a continuous approach, so we need a continuous function. Okay, it's a kind of interpolation between the two original functions. and we have this eta. Sorry, it's eta again. It's not the same as before. This is a parameter that controls the smoothness of the curve, okay? By changing eta, we can have a very smooth transition or more steep transitions, okay? And for this system, specifically for Saccharomyces cerevisiae, the Saccharomyces cerevisiae cell wall, we have no charge in one of the mediums. We have no fixed charge in one of the mediums, so the media. So it is 0 here, and we get this expression, okay? So by introducing that volumetric charge density of fixed charge, we have the whole picture here. And here we have the concentration, the equilibrium expressions. We use the Boltzmann distribution. We sum up all the contributions, and we get here the expression for the fixed charge density, the volumetric charge density of fixed charge. Okay, so this is the whole this is the Rho expression, and this is added to the Poisson-Boltzmann equation. And using the same approach, we have simulated also, tried to predict also the electrostatic behavior of gram-positive bacteria. Okay, so the same approach, we have here the cell wall and the external function. So we use again the smoothing function here. This is the extracellular environment. Okay, the structure is different comparing the yeasts with bacteria, but we can use the same model, only changing the groups present and the density of sites. Okay. So these are some results that we got for different pHs. We have here the electrostatic distribution for those different pHs. We can see here that it goes fast to the bulk values for each pH. And we can come from a positive potential to a negative potential because of the charge regulation. Because of the protonation and deprotonation of the protein. This is not protein, sorry. Yeah, the protonation and deprotonation of the proteins, of the groups that are present in the cell wall, the bacterial cell wall. And from this, we can predict the so-called Zeta potential. Zeta potential is the potential, the surface-like potential that is really measured. Because when we do an experiment, an electrophoretic experiment, we apply electric field to the solution, so that, for example, let's say that we have negatively charged particles, and when we apply that electric field, we get, for example, movement of these charges, of these particles. And from the movement of these particles, we can estimate the Zeta potential that there is a kind of surface potential. It's not exactly the surface potential because together with the particles, there is some molecules of solvent and also ions that move together, and thus limit, location in space that limits what moves together with the particle and what is not moving with the particle is the so-called shear plane. So the Zeta potential is the potential at the shear plane. Okay, so it's a distance from the real interface. Because we can, because of this, we cannot measure directly the surface potential. So that's the potential that we can measure experimentally. That's why we considered here distance equal to, in this case, we considered equal to the, in some case, the Stern distance. That would be this delta here, in order to compare with experimental results. Okay? And just before discussing that, zeta potential is a very important property because it's related to the colloid stability. If you have a high magnitude of zeta, depending on if it's positive or negative, you have a higher electrostatic repulsion, guaranteeing stability, okay? And here's the comparison between our theoretical results, computational results. In this case, without adjusting any parameter, this is predictive. So this is the comparison of our results of zeta potential in different pHs with experimental results. Unfortunately, for this case, we didn't have the values of uncertainties of the experimental results, but we can see that it's quite good prediction. It's a quite good prediction. So we thought, oh, maybe we can apply the same theory for yeasts, for Saccharomyces cerevisiae, for example. This worked quite well for Bacillus brevis, gram-positive bacteria. So let's see how it works for Saccharomyces cerevisiae. This is one of the results that we obtained. We can see that it's not that good as for bacteria. And we had to, in this case, also to adjust some parameters. So we adjusted the pKa's, and we had also to consider an effective parameter here, considering that not all the groups, if I'm wrong, Natalia will correct me today in the afternoon, we considered that not all the groups are available for contributing to the surface charge or the volumetric charge, depending on the model that we are considering. So in this case, it's not a predictive model. It's a kind of semi-phenomenological model, okay? But we get good results as well. And I'd like to finish acknowledging my collaborators. So there are many collaborators engaged in this line of research. Ana Cristina Araújo, our master student that just defended last month her thesis. Drew Parsons, there is a colleague that works with us for a long time, since 2007, I think. Evaristo, that was my former supervisor. Frederico Tavares, that was my former supervisor as well, and still works with us. Genjo Wu, that was my supervisor during my postdoc. John Prausnitz, I had the honor of publishing a paper, those results that I showed for protein interactions, I had the honor of publishing with John Prausnitz. There's a very well-known thermodynamicist in chemical engineering. Matthias Bostrom, a friend of long time as well, since 2005 working with us. He is Swedish, but he's now working in Norway. Marlon Gama, a PhD student. Natalia Barbosa, that is here. She's my colleague now as a professor at UERJ, but when she was our PhD student, she got most part of the results that are presented here. Mirella Simões, another PhD student, former PhD student that worked with Fred, and my colleague Pedro Alijó that works at UERJ as well. And I'd like to thank for the financial support of different agencies, and I thank you for your attention. Okay, we have time for questions. I know you were hungry, but maybe you have some questions. Yeah.
When you're working with those lysosomes, I was just curious why you were able to work at low pH as opposed to.
It was the pH where we had the experimental results. So that was the reason. We are doing simulations, and I don't know why, but the pH where we had more results were 4.5.
Because it does change the confirmation, right? So
yeah.
Okay.
Yeah. We are not considering conformation, so maybe in other pH it wouldn't work so well. But we didn't test that because we didn't have so many experimental results. Okay. More questions? Okay, so we can go for lunch. Thank you very much.
So guys, we are free to go for lunch now. I'm going to ask you a favor. I mean, in principle,